So today we start with the kinematics of rigid bodies, and in particular we're looking at rotation about a fixed axis of a rigid body. So first of all, let's talk about the differences between rigid bodies and particles, which we've been studying. So with a particle, it doesn't matter what its size and shape are. We looked at a lot of objects as being particles. The only thing that was really important about it was the mass. So for example, when we looked at a car traveling on a road, we didn't really care how the car's mass was distributed or what its wheelbase, any of that kind of thing. Again, mass was important for kinetics, but the size and shape didn't really matter, because the motion is just translation. It could be translation along a straight line or along a curved path, as we looked. But the difference, of course, is that when we have a rigid body, as we'll see in a moment, we can have rotation as well. So for a rigid body, now the size and the shape are important. And when we get into the kinetics part of this, not only the mass, but how the mass is distributed is important as well. And so, as we said earlier, the motion, well, it can be translation just like it is for a particle. It can be rotation, or it can be both of those things combined at the same time. Now, if we look at translation of a rigid body, well, it's exactly the same as particle, because now we're only looking again at translation, then the size and the shape don't matter. And so as far as the kinematics go, we don't have to do anything there. We treat it just the same as we would treat a particle. Then we can look at today's topic, which is what if that rigid body is rotating about a fixed axis. And then the next category is called general plane motion, which means that you have both rotation and translation going on simultaneously. So we're talking about rotation about a fixed axis, and so I've shown a link here. It could be a wheel, it could be any shape of an object that's rotating about a single fixed axis, or an axis going through a point where this is pivoting down on the lower left here. So we define its motion then by the angular velocity, and instead of using theta dot, we tend to use omega for that. And where we were using theta double dot before for the angular acceleration, we tend to use the Greek letter alpha for that. So omega is velocity and alpha is acceleration. Now let's look at the velocity of a single point. In this case, we'll look at the hole that's on the other end of this rotating link, and that point is going to be r away from the axis. Then the velocity is simply r times omega. So just like using normal and tangential components here, the velocity, which would be r times theta dot, or r times omega. And of course, there are going to be two components of acceleration of that same point. The tangential component would be r times alpha, and the normal component is r times omega squared. We would write the normal acceleration before, when we were looking at particles, as being v squared over rho, but in this case rho is r. V, as we said, was r times omega, so v squared over rho would be r times omega squared. Now some of our problems will look at gears, or belts and pulleys, and in the case of two gears that are in contact, they're going to be rotating in opposite directions. The gear teeth, so you can think of gears as being two cylinders that are in contact that don't slip, and what the gear teeth do is to make sure that there's no slipping. And what that means, of course, is that the velocities of two mating points have to be the same if there's no slipping. And so using that, we can show that the ratio of the angular velocities, omega 2 over omega 1, is equal to the ratio r1 over r2. So the smaller gear is always going to be turning faster than the larger gear. And similarly for the accelerations, you have the similar relationship, where the angular acceleration of 2 over 1 is also the ratio of the radii. And with gears, it turns out that the gear teeth have to be the same size. So instead of looking at the radii, we can also look at the ratio of the number of gear teeth and have exactly the same ratio. So next time we'll build on this, what we just learned about rotation about a fixed point, and look at the case of general plane motion, where we have both translation and rotation going on at the same time.